Okay, so imagine this for a second. You're holding a high-powered rifle, and you aim it at a cloud, just a big fluffy cloud in the sky, and you pull the trigger.
Right.
You'd expect the bullet to just zip right through. I mean, it's just missed. But instead, the bullet hits the cloud and bounces right back at you.
That would be startling, to say
It's
the least.
startling. It'd be impossible. You'd think you were going crazy. But that's pretty much the level of shock physicists felt back in 1909. We're going back to a moment that just fundamentally broke our understanding of reality.
It's the birth of nuclear physics, really.
Exactly. We're talking about the moment we all realized atoms aren't just solid little balls or smears of jelly, but these complex, structured things.
And that's our mission for this deep dive. We're going to unpack the famous Rutherford scattering experiment. It's all about how shooting some particles at a thin piece of gold foil managed to completely rewrite the science textbooks.
We're working from a great lecture, Quantum Computing with Anna, and what I love is that it doesn't just give us the history. It really breaks down the physics, the math, the actual mechanics of how it all happened.
Gets into the gears of it. And the source really highlights the elegance of the logic. I mean, yeah, the math can get a little heavy. We're talking differential equations and all that. But the core idea is just beautiful. It's a detective story where the main clue is a tiny particle flying off in the wrong direction.
Okay, so let's set the scene. It's 1909. What's the world of physics even look like? Chemistry had a pretty good handle on atoms by then, right?
Oh, yeah. For chemistry, it was well understood. They treated atoms as these tiny point-like objects. And that model worked perfectly for, mixing chemicals, calculating gas pressures, all that stuff.
But physicists wanted to look under the hood.
Of course, they're physicists. They're never satisfied with a black box. But the main theory at the time, well, we can call it the smeared out model.
Yeah.
You might know it as the plum pudding model.
Right.
They knew atoms had positive charge because electrons are negative and the whole thing is neutral. But they figured that positive charge was just spread evenly throughout the whole atom, like dough.
So really low density, like jam spread on toast or something.
Or a very, very thin cloud. And if that positive charge is all smeared out, it's not dense, it's soft. So if you shoot a high-speed particle at it,
it should just punch right through.
exactly like your bullet through the mist, there's just not enough concentrated stuff in any one spot to put up a fight.
Okay, so that's what everyone's expecting. Now enter our main characters, Hans Geiger and Ernest Marsden.
Right. These were the two individuals who were really driven by this curiosity. They were working for Ernst Rutherford, and they set up an experiment to test this soft atom theory. They needed a bullet and a target.
Let's start with the bullet. The source calls them alpha particles. What exactly are we talking about here?
So an alpha particle is basically just a helium atom that's been stripped of its electrons. It's a helium nucleus, so 2 protons, 2 neutrons. And since they've lost their negative electrons, they have a positive charge, a charge of +2. They're heavy, they're positive, and you can fire them in a beam.
So compared to a tiny little electron, these things are tanks.
Absolute tanks, yeah, thousands of times heavier. And they were moving really, really fast. The idea that some soft atom could stop one was, it was almost laughable.
And the target for these tanks?
Gold foil, but extremely thin. The source notes it was beaten down until it was only a few atoms thick.
Why gold, though? Is it just because it's valuable?
Not really, no. It's because gold is incredibly malleable. You can hammer it thinner than just about anything else without it breaking apart.
Yep.
And they needed it to be as thin as possible.
Why was that so important?
So that the alpha particles would, ideally, only interact with one atom at a time. They didn't want to shoot into a brick wall. They wanted a clean, single collision.
Okay, so we have a beam of these alpha particles hitting a super thin sheet of gold. What were Geiger and Marsden actually doing?
It was tedious. They were recording the angular distribution.
Yeah.
Basically, they had to sit there and count where each particle went after it hit the foil.
Did it go straight? Did it veer off to the side?
Exactly. And when you say count, you mean literally counting. They had a screen coated in zinc sulfide, and when an alpha particle hit it, it made a tiny flash of light, a scintillation.
Wow.
So they had to sit in a pitch-black room, let their eyes adjust for like half an hour, and then stare through a microscope and count these little sparks.
Oh.
1 by 1.
That is just unbelievably painstaking work. The patience.
It was grueling. But it's how they built what's called a differential cross-section.
That sounds complicated.
It's a fancy term, but the idea is simple. It's a probability map. You just put numbers to the angles. You count how many particles end up at 10 degrees, how many at 20 degrees, and so on.
So it's asking, if I shoot a particle, what are the odds it ends up over here?
Precisely. And according to the old smeared-out model, the odds of it ending up anywhere but straight ahead should have been tiny,
Mm.
almost zero.
Let's visualize this. The source uses a cloud chamber image, which I think is a great way to see it. You have an alpha particle zooming in, and then, bam, it gets near a nucleus and just veers off.
It scatters, yeah. And that angle it flies off at, that's theta, the scattering angle. But the source points out a crucial detail in that image that's easy to miss. The nucleus itself recoils.
Wait, the gold nucleus actually moves?
It has to. I mean, in the image they show, it's probably a lighter gas to make the recoil obvious, but the principle is the same. The nucleus isn't infinitely heavy. It's heavier than the alpha particle, sure, but it's a collision. It gets a little push.
So it's like a billiard ball hitting a bowling ball. The bowling ball barely moves, but it does move.
That's the perfect analogy.
Right.
And it proves we're dealing with two distinct objects acting on each other. It's a dynamic event.
Okay, so back to the actual results. As everyone expected, most of the alpha particles just flew straight through.
Right. Which makes sense if the atom is mostly empty space, like shooting at a chain link fence. Most bullets will just go through the holes. But, yeah, a small number didn't. Some were deflected at pretty large angles. And this is the shocking part. A tiny fraction, about 1 in 8,000, were reflected directly backward.
And there it is. That's the bullet bouncing off the cloud.
That's the smoking gun. If the positive charge was smeared out like jelly, a big, fast alpha particle would just plow through it every single time. The only way you get a bounce back is if that particle hits something incredibly dense and hard.
The nucleus.
The nucleus.
Yeah.
That 1 in 8,000 event proved that the positive charge wasn't spread out. It was crammed into a tiny, massive core. The atom wasn't a cloud. It was the rock surrounded by a whole lot of nothing.
That is amazing. The entire field of nuclear physics born because a few particles made a U-turn. So let's dig into the why. What force is strong enough to do that?
It's the electrostatic force, or repulsion, to be specific.
Right, because both are positive.
Exactly. The alpha particle is positive 2. The gold nucleus is positive 79, like charges repel. And it's what we call a central force that follows an inverse square law.
Okay, inverse square law. We hear that phrase a lot. What does it actually mean for our little particle?
It just means the force gets strong really, really fast the closer you get. If you cut the distance in half, the force doesn't double it, quadruples. So the alpha particle is flying in, feels a little push, then a bigger push, and then suddenly it hits this massive wall of force that just flings it away.
The source gets into the actual equation, right? It starts with EFMA and then brings in Coulomb's law.
It does. It's an intimidating-looking equation, but the parts are simple. You have Q1 and Q2, which are just the charges of the particle in the nucleus.
And then there's that epsilon naught thing. The source called it a magic number.
It kind of is. It's the permittivity of free space.
Honestly,
You can think of it as a conversion factor that just exists to make our human-made units of measurement work with how the universe actually is.
Got it. And there's a vector in there too, r hat.
R hat just points the way. It tells you the direction of the force, in this case, pushing straight out from the nucleus toward the particle.
Yeah.
A repulsive push.
So we have the equation. How did they actually use it to figure things out? The source says there are 2 ways to solve the problem.
Yeah, and this is such a cool insight into how physics works. There's the hard way and the clever way.
Right.
The hard way, which Rutherford's team probably did first, is all calculus.
The heavy lifting.
You got it. Differential equations. You use EFMA to calculate the particle's position at every single tiny instant of its journey. You trace the whole curve. It works, but it's a mathematical grind.
And the clever way.
The algebraic way. This is brilliant because it's kind of lazy in a smart way.
Yeah.
It just ignores everything that happens during the collision itself. It only looks at the before and the after.
So it just cares about the particle coming in from far away and where it ends up far away.
That's it. By using conservation laws, conservation of energy, conservation of momentum, and some high school level trig, you can get the exact same answer without solving a single differential equation.
That feels like cheating.
It's the power of conservation laws. If you know the rules of the game, that energy can't just appear or disappear. You can predict the outcome without watching every single move.
So no matter how you solve it, the path the particle takes has a specific shape, which the source calls a hyperbola.
A hyperbola, yes. It's the path of something that comes in from infinity, gets deflected by a central force, and flies back out to infinity, never to return.
And it has these foci, these focal
Right.
points.
And the gold nucleus sits right at one of those focal points. The math of the inverse square force just locks that geometry in. The particle has to follow that specific hyperbolic path.
Okay, there was another term the source focused on that I think really helps visualize this, the impact parameter.
Yes, this is so important for understanding the results. Just imagine for a second the alpha particle had no charge. It would just fly in a straight line. The impact parameter, which we call B, is just the distance between that imaginary straight line and the nucleus.
So it's how far off center you're aiming.
Perfect way to put it, yeah. If your impact parameter is 0, you're aiming straight for the nucleus. Head-on collision. That's the particle that bounces straight back at 180 degrees.
And if the impact parameter is really big,
You're aiming way off to the side. The particle zips past. Maybe it gets a tiny nudge from the force field way over there, but it basically goes straight. And that explains why most of the particles were undeflected. They had large impact parameters.
so the whole experiment was just a game of chance, hitting all possible impact parameters.
Exactly. And the fact that so few bounced back told them the target, the nucleus, must be incredibly small. If it were big, a head-on collision would be easy. The fact that it was so rare meant the nucleus had to be tiny.
I want to throw in one more term just because it sounds cool. Periapsis.
Periapsis. It just means the point of closest approach. Even in a near miss, there's a moment where the particle gets as close as it's ever going to get before the repulsive force wins and pushes it away. That's the turning point.
So bringing it all together with the results. The simulation data in the source shows this huge spike at 0 degrees, all the particles flying straight, and then this tiny, tiny, but definitely not 0, line at 180 degrees.
The bounce back. That little line at 180 is the data point that changed everything. It confirmed the atom has a massive, dense core. All the math, the hyperbola, the impact parameter, the force, it all clicked into place to explain that one tiny result.
It's just wild. Before this, the smeared out model was just what everyone believed.
And it wasn't a stupid model. It explained what they could observe at the time. But you have to test the boundaries. And this experiment was an extreme test that the old model just couldn't survive.
So what's the big takeaway from all this?
I mean, the takeaway is that this experiment gave us the model of the atom we know today. We went from a blob of jelly to a miniature solar system with this dense nucleus and electrons orbiting. It literally launched the entire field of nuclear physics.
The original particle collider.
In a way, yeah. It set the whole precedent for what they do at places like CERN. Smash things together and see what comes out. It shifted physics from just observing nature to actively interrogating it.
And I love that they never actually saw the nucleus. They couldn't. They just saw its effect on something else.
That's a fantastic point. They mapped an invisible object by seeing how it deflected projectiles. It's like trying to figure out the shape of a statue in a pitch-black room by just throwing tennis balls at it and listening to where they bounce.
And the statue turned out to be really small and really heavy.
And surrounded by a whole lot of empty space.
Before we go, I want to circle back to something you mentioned earlier, the recoil. The fact that the nucleus itself moves a little when it gets hit.
Yes. It's a subtle point, but it's profound.
It makes me think about observation itself. You know, we think of looking at something as passive, but here, to see the nucleus, they had to hit it with something which changed its state. It moved.
It raises a really interesting question for you to think about. If the only way to observe something on this scale is to interact with it, to hit it with a particle or a photon of light, and that very interaction changes the thing you're observing, can you ever really know what it's like when you aren't looking?
Are we just measuring the interaction itself?
Or are we always just measuring our own impact on the world? It's the core dilemma of quantum mechanics, and you can see its shadow right here, back in 1909. The act of measurement is not passive.
That is a lot to chew on. Well, on that note, we'll wrap up this deep dive into the birth of the nucleus.
It's a great reminder that sometimes the biggest revolutions in science come from the tiniest, most unexpected results.
Thanks for listening, everyone. Keep asking questions, and we'll see you on the next deep dive.
What?